Okay, eventually I want to tell you about this strong, to my view, connection between imprecise probabilities and causal analysis. I'm shameless because this is most of these results, let's say the theory is the consolidated theory of causality à la paire. But the connection is something we did with my colleagues at IDSIA in the last two years. And wait a second. As you might guess, my approach to causal analysis is basically Bern's approach. I think it's very convincing, it's very readable, it's very much in the track, and of course it should be in the track of probabilistic graphical models. The black book you can see on the top is the book was already cited by Fabio, by Cassio, where the main theory of Bayesian network was established long time ago. The green book was the first book on causality by Bern. Maybe my suggestion, if you are interested in causal analysis, is if you want to know the general stuff, maybe you can consider the book of why. But if you really are interested in doing research in causal analysis à la paire, I think this white book, the primer, is really the best reference you can find. Okay, I already discussed this ladder of causation. Witty font is a kind of metaphor of, let's say, the three levels of knowledge we can consider, we can access. And okay, my point with this talk is that imprecise probabilities, and more specifically critical networks, can be a very valuable tool to move up in this ladder of causation. My point this morning was that machine learning is mostly on the first level, is mostly on association, on observational prediction. We want to move up. And critical networks can help on that, and can also, from a technical perspective and also from a philosophical perspective, in the way you conceive the model, you might have a better view of this kind of system if you come from this community for the set of models. I said I'm shameless. I'm mostly referencing to stuff I did at IDSIA with my colleague, mostly Marco Zaffalon. All this idea basically come from some of his intuition, and Rafael Cabañas, who is now with the University of Almeria, but he started working with us almost 2 years ago at IDSIA. We have some papers. We have a software, which I'll try also to, a Java software, okay, which is based on another Java software for critical networks. I also try to advertise. We are working on the Python version. Java may be for some other people, for some people, it's not the most friendly. We are trying to do reporting in Python, but the Java software is already well documented, very relatively easy to use. Let me say also that my background is mostly in critical networks, and that's why also I like so much this topic, because I worked a lot in this field. I used exactly as Cassio did, as Fabio did, as other people did, in application, the theory and the application of critical networks. And critical networks have been used a lot in decision support system. I'm working with the Swiss Army, developing a system for military decision-making, this kind of stuff based on critical networks. I'm very interested in this robustness analysis of machine learning algorithms, especially when based on graphical models, in the spirit of what Cassio was mentioning, for instance, about the naive critical classifier. Okay, but in all these cases, let's say the imprecision was the result of adding robustness, checking whether the results were robust or not with respect to perturbation on the parameters, or in the case of system based on knowledge, the precision was trying to capturing the fact that it might be very hard for an expert to express his or her knowledge in terms of sharp numerical probabilities. So we were using intervals because it might be difficult for an expert to express the knowledge in terms of a sharp number, while an interval can do a better job. But okay, still, the adding imprecision to the system was a kind of external action. Well, I think in these approaches, in causal analysis, because of the presence of latent variable, the role of imprecision is intrinsic. If you want, is exactly the same that happens when you cope with missing data. If you cannot do specific assumption about the reason for your data to be missing, it's very natural to put there this kind of imprecision, and somehow this is exactly the same happenings in these techniques. Okay, let me say that we did, not only me, Cassio, these people, also other people, a lot of research in critical networks, especially on inference algorithm and complexity analysis. And somehow, after many years, I can see, let's say, this stuff to be used in a very different topics. I think the kind of optimization we are already did in the specific context of critical networks can be used now in the context of causal analysis, and more specific, as I'm going to discuss, in the case of counterfactual analysis. Somehow there is also a cross-fertilization, and also it happens the other way around. So what we did in this field can give us idea about how to improve inference with critical networks. For instance, Cassio was blaming sampling with Bayesian, sampling the Bayesian networks of the critical networks. It's still very preliminary. I see you already disagree, but I think we got a message that in some way sampling for a lot of you see this point of Cassio. Okay, a critical network is equivalent to an exponential number of Bayesian networks. In principle, you can pick some of these Bayesian networks, compute the inference. Each inference will be a point, and then consider, for instance, the interval spanned by this point. And this, by definition, is an inner approximation of the true interval. But it can be a very bad. Why? Because the number of points you need to sample is very huge. That's true, but what there is in between is a kind of projection, because we are not coping with the joint model, we are coping with a specific interval. So, and we have some confidence results which can give us some hope to this direction that for a lot of time we consider hopeless. But this is just to say that there is a kind of cross-fertilization between the two directions. Okay, let me start with this minimalistic example. So I need to define some language, some common language. This is more the standard theory of Perl, but by means of this small example, you can already see the connection with Imprecise. Okay, we distinguish between endogenous and exogenous variables. The endogenous variables are the variables of our system. So by definition, they are manifest. We can observe this variable. So in this case, I have a single endogenous variable, which is x. Say that x is a Boolean variable. Say that we can collect observation for this manifest variable x is Boolean, so we can, our statistical analysis tell us that the probability of the first state of this variable is p or whatever. Okay, so this is kind of empirical knowledge we obtain from a statistical processing. Now, let's say that we have also another variable. Let's say this variable is u. U is a quaternary variable. And U is what we call an exogenous variable. So somehow it's not part of our system. It's connected, you will see, to our system, and is a latent variable. It's typically a variable we cannot observe or we don't observe. And the connection between the two variables is deterministic. So there is a deterministic function that for each state of U determines the state of X. You see? So we have 4 states of U. For the first states of U, we get the first state of X. For the third and the fourth state of U, we get the second state of X. It's just a very simple function. We typically want this function to be subjective, so to cover all the possible values of the output. Not necessarily the function should be invertible. So it should not necessarily be a B action, and typically it's not going to be. Okay, this example is so small that it's not especially interesting. So why do I need the 2 different states of U to generate the state of X? the thing is going to be more interesting, more complicated setup. But it's just to show you the rules of the game. And okay, we can regard X as a deterministic function of U, but we can also use the language of probabilities, of conditional probabilities. So if X is a deterministic function of U, the conditional probability of X given U is known, is a degenerate conditional probability table or whatever. So for each value of U, this X is going to be 0 for all the values apart from the one corresponding to this value of U through the function X. So basically it's a delta. You see, these are the rules of the game. This is in the spirit of Bayesian networks. This is in the spirit of structural models, you will see, but basically I say. And what I'm using here is just the total probability theorem. You see, I'm expressing the marginal as a conditional weighted by the probability of U, and I sum, sorry, this was a, yes, this was a sum over U, not over X, sorry. But you see, okay, this is a relation, this is a constraint. Remember that P of X is known. We have observations, so we know P of X for each state. P of U may be unknown. Let's assume that we have the data about X, we know P of X, but we don't know P of U. So we ask ourselves about which is the specification of P of U compatible, consistent with P of X. And the second question can be, is there a single one or more than one? Okay, one possible value, we know that the probability of the first state is P. So we see that the sum of the probability for the first two states of U should be P, and all the rest should be 1 minus P. But of course, we can distribute the mass of probability P over the first two states of U in different ways. So my point is that there is an infinite number of specifications of P of U, which is consistent with the P of X we observe. So these naturally produce a Credal set, which is K of U. I'm parameterizing this, you see basically this is the set of all the quaternary distributions such that the sum of the probabilities on the first two states is P. And so this is already my point. I could stop. If you are tired, I'm going to stop. I'm not probably going to stop, but this is, from my point of view, one of the most important points. So in causal analysis, at least in causal analysis at Perl, we have a deterministic relation between latent variable, and which we call exogenous, and manifest variable, which we call endogenous. We have endogenous observation, we have an endogenous probability data, but this data can be shaped as a probability mass function. And basically what we can do is back propagate this information back to the latent variables and get the P of U. But because of the non-bijective nature of this structural equation, this is a one-to-many, it's not a one-to-one. So we are not from the P of X, we are not getting a single P of U, but a set of P of U, a Credal set, if you want. And that's why imprecise probabilities are part of the game. Is it clear? Of course, this is what people call a structural causal model. Okay, this is somehow the simplest, is the smallest structural causal model you can consider. Okay, more generally speaking, we have a set of endogenous variable and a set of exogenous variable. And we have a graph describing the relation between these ones. There are many formalisms. Sometimes you can see this P of this U, which is, for instance, this is a latent variable, which is the parent of two manifest variable. Sometimes people just use the bidirected graph without explicitly showing the U variables. But basically, this kind of graph are expressing the relation between this latent and these manifest variables. Okay, to define a model, we assume that the children are determined, deterministically, the states of the children are deterministically obtained through a structural equation. A structural equation, which is an equation of the parents. In my example was just U, but generally speaking, there will be U variables and X variables part of the game. And in this case, the direction of the arcs matters. This is already a causal model. So it's not like in the case of Bayesian network, where the arc is just showing a correlation between the two variables. Here we have a deterministic relation, so a causal relation. So it's not possible to invert the arcs, especially because these functions cannot be inverted. Okay, a typical assumption is the semi-Markovian. Let's say we copy with this assumption. So these latent variables are assumed to be the root of the graph, the parentless node of the graph, while the other variables are the X. So this is the typical setup of structural causal models. So the ingredients are the graph, the equation, one equation for each manifest variable, and as we want to define a probabilistic model, at least in principle, when possible, a marginal probability of P of U for each one of these latent, or we call them exogenous variables. So these are the three ingredients of these models. And if you want, this is just a special case of Bayesian network. If you remember Cassio, in the case of Bayesian network, we should define for each variable a conditional probability table or whatever for the variable given the parents. For the parentless variable, we have the P of U, which is already the margin because they have no parents. For the X variables, we have the probability of X given the parents because this is the equation is already given the specification, the degenerate specification because it's made only of 0 and 1s of the conditional probability. So this is a proper Bayesian network specification. And so your question can be, okay, why people is interested needs a different name? Why this seems to be just a special case of Bayesian network. And they are, but in standard setup, the P of U's are not available. So this will be, with the P of U's, this will be a fully specified structural causal model. But in practice, we don't have the P of U. We have some information which is related to the P of U because the P of U are the source of the uncertainty in our model. But it's something we cannot observe, or we can observe indirectly at the level of the X variables. So the challenge for us will be somehow to back propagate. So given the information about X, to go back to the uncertainty on the PDU. Please, Gatti.
Alessandro, in your example, the model for you was completely monotone, right? Because you specified some the special model that you had there. It's a technical, yeah. So it's completely monotone. It's in the sense of belief function.
Yes, yes, and in fact, this is a general fact. You will see that I will mention later that it's the clear set we cope with corresponding are belief functions.
Okay, that's always the case. Okay.
Yes, yes, and it's not surprising as you saw already. We'll mention that later. Okay, let me also please.
Belief function in the sense of the depth share.
Yes, yes. I will say something more a bit later. Yes. There are clear sets, but because of these determinism, the subset are a special class of clear sets, which, if you want, is not that helpful from the point of view of inference, because as you might get from Cassio, when you need to compute inference in clear networks, what matters are, let's say, the number of vertices. You have all this combination. There is a bound of the number of extreme points of this special class of clear set, which is the factorial, but the factorial is basically exponential. So is, let's say, from the point of view of inference, this remark is not that crucial, but I think it's interesting, and it tells you something about this idea of progress. But I plan to say something also about that later. And okay, I'm focusing on the discrete case. What we did technically was focus on the discrete case. It seems that the continuous case is quite analogous. There are some technicalities which might make things more boring and more complicated, but somehow the same ideas you can apply to the continuous case. So here, for instance, you see Z is the sum, which is still a deterministic function of X and Y. I said that X and Y are continuous or whatever. Okay, so these are structural models, and these are the models we want to use for our causal analysis. But okay, let's go step by step. Remember, we have a ladder, so let's go step by step, and let's start from this tuple. We have just two variables. These variables are manifest, so are something we can observe. Is there the first variable is taking or not taking the aspirin, and the second variable is ADH vanishing or persisting in spite of taking or not taking the aspirin. So we have X and Y. Okay, maybe we took the aspirin and no ADH after aspirin. So which is the probability that this has been due to aspirin? Okay, we can discuss about this question, but let's say that we just have observation. So we have a data set, crazy data set about us taking every day or not. I don't know. But okay, from this data set, in principle, we can compute these conditional probabilities for the two scenarios and say that, okay, it seems that is more likely to still have ADH when we don't take the aspirin or something like that, because this probability is bigger than the other one or something like that. Okay, is this a conclusive analysis from our perspective? Probably not. This is definitely not a causal analysis. This is based on this observational data. This is based on the correlation between X and Y. And we know example, if you check this primer of Perl, you can see okay, but also not in this, also in earlier books, you can see lots of examples where these kind of conclusions are misleading. So for instance, very often you have this kind of relation, then you consider another covariate, so you condition also on an additional variable, and everything is completely different. I like actually this example. I don't know if you are familiar with it. This is cholesterol and exercise, and it seems that the more exercise you do, the more cholesterol you get. These are the aggregated data. It sounds a bit counterintuitive, and in fact, it's not like that. These are stratified with respect to the age. So it happens, at least for these data, that, okay, people in their 20s, you have the expected pattern for each level of age, but probably people, as they get older, they start to be concerned about cholesterol, to do more exercise or something like that. But okay, if you want, this is an example of the so-called Simpson's paradox. There are lots of cases like that. It's very funny, it's very interesting, but okay, it's telling us also that we cannot always trust this kind of, so probably we need to move up in the ladder. And okay, to move up, let me consider still the aspirin example, but with an additional variable, which is Z, which is the gender. But okay, I'm not entering the details. So let's just say that we have an additional variable Z. Still, this is a structural causal model. Okay, this is what we call a Markovian structural causal model. Markovian means that for each endogenous variable, there is a single U variable, a single U parent. Okay, so we might have to see, for instance, that Y is determined by X and Z, but also by U of Y. And each manifest variable has a latent parent, which is the source of uncertainty, because it's determined by the structural equation. Okay, now let's say that for some reason I force myself or force another person to take the aspirin. Is this different from the situation in which I observe the fact that I took the aspirin? Of course it is, and this is what people call intervention. And the notation used by Perl is this do operator. So do of X of equal to 1 means that I do an intervention on my system. I ask the patient or whatever to take the aspirin or whatever. And now I'm interested in how my beliefs about having or not having ADH are changed by this. And at least in general, these updated beliefs are different from the ones conditional to the observation of the fact that I took the aspirin, at least in general. So we are interested in interventional queries. Doing an intervention from the point of view of a structural causal model means to change the equation, because now the equation is like a constant. No matter which are the inputs, the equation is always giving as an output the fact that you took the aspirin. So doing an intervention means at the level of the structural causal model to change the function, and from the point of view of the graph, basically to remove the incoming arcs. So this is, and this operation is called the surgery at the level of the graph. And once you do the surgery, you can compute the probability of the variable of your interest given the intervention exactly as if it was an observation. So this is smart because in this way, after the surgery, we can reduce our query to an observational query. And the problem seems to be solved, but not always. Actually, this idea, together with the disseparation concepts discussed by Cassio, is what people call the do calculus. And the do calculus is a graph approach to reduce an interventional query to a set of observational queries. This is an example. You see, I'm doing intervention of X. Because of that, I'm doing this surgery. And now I can compute this interventional query as an observational query in this graph. And this, if you want, can be expressed like that. And this is nice because this is not involving the U variables. So this is something I can compute by only using the data. And this is what do calculus is doing. And basically, do calculus only needs the graph, not the structural causal model, not the marginal probabilities on the U we need for a complete quantification of the structural model. This is the point. So we have a clear advantage in the do calculus. So this is just an example of a package, of an R package, but they are lost because it's a pure graph algorithm. You just have to do manipulation. Eventually, the do calculus library will tell you, okay, you have to do this computation. I need this probability, this probability, this probability. You can compute this probability from the data set. Somehow, for instance, you can learn a pure observational model like a Bayesian network, compute this probability, do the formula, whatever, and you get the result. But you get the result of an intervention. So everything looks very easy. In principle, an alternative is to do that directly in the structural causal model. Well, you also have the P of U, but typically you don't have the P of U. The issue is that this is not always possible. When this is possible, we say that the query is identifiable. Do calculus is sound and complete. This can be proven. This was proved. And basically this means that is an if and only if. If the query is something you can compute, you can use do calculus. But there are queries that cannot be computed. These queries are called unidentifiable. And if they are not identifiable, basically you don't have key to get that, at least by means of this machinery. Okay, an emerging idea is that the unidentifiable queries are partially identifiable. So in fact, the value of the interventional query, the probability of the variable of interest given some intervention, is something which is not precisely specified. And we are going to formally see that this is the case. And this is not surprising for us, because actually we already got the intuition that on the U level, on the latent level, we have imprecise probabilities. So we know that the result of an inference is basically the result of an inference in a equivalent network, so it should be an interval. But do calculus is not able to do that, because do calculus is trying to reduce the result of this query to a precise computation based on the data. There are cases in which this is not possible. So for instance, here, if we do an intervention of X2, basically we still have this latent variable which is confounding x2 and x3, and so this query is not identifiable. And we should expect, at least in the general case, an interval as the result of this query. But the traditional techniques are not able to do that. Okay, people is in the very last year is working, these two guys, Elias Barenboim, Julia Perle is the founder of all this stuff. Elias Barenboim was one of the students of Julia Perle and is the one more active. Now he's in Columbia, he's probably the person more active in the field of causality and in the field of the application of causality to machine and reinforcement learning. His group is publishing an impressive number of very strong contribution. SIPTA is another former student of Julia Perle, which is another group, and all these people is moving in this direction because partially identifiable queries are interesting, and these queries are especially, we want to use, of course, imprecise probabilities for that, but I want to say that partially identifiable queries are especially interested because they concern to the third level of the ladder, which is the counterfactual. So the counterfactual level. So let's move up, and now let's ask a genuine counterfactual question for ourselves. What if I had not taken the aspirin? Would I have edge state or not? So you see, if I had not taken, is a negative intervention, but it's still an intervention. But we say that it's counterfactual when there is a contradiction because between what we did in practice and what we observe. No, sorry, what we observe in the reality and what we think. So it's like we are considering two different worlds. The real one, where there was something, and the alternative one, where something contradicting what we observe is happening. And so you can already see that the traditional technique, even the graph we are considering so far, is not enough because the graph is made of a single realization of our x variable. And our x variable can be 0, can be 1, but can be simultaneously 0 and 1. So we need some kind of more complex structure. Of course, these objects are, this is a typical counterfactual query, is the so-called probability of necessity. And its probability of an effect being, for instance, false, given that we did an intervention making the cause, let's say the cause X, false, and this would be like the alternative world, given that in the real world we had a positive observation for both the variables. So you see, and this so far we don't know, even if we know the surgery, we don't know how to compute this guy. And we don't know how to compute this guy because we have x equal to 0 and x equal to 1. So we need a kind of auxiliary structure, which is based on the structural causal model. So if for intervention, second layer, we need the graph. For counterfactual, okay, for counterfactual analysis, we need the structural causal model. And eventually we need to augment the structural causal model by basically duplicating the manifest variable. Because we need the manifest variable in the real world and the manifest variable, a replica of the manifest variables in the alternative world. But if the structural causal model is specified, we can use these auxiliary structures, which are called sometimes twin networks, sometimes counterfactual networks, to compute counterfactuals. An interesting remark is that you can prove that apart from trivial cases, counterfactual queries are non-identifiable, or in our language, partially identifiable. And that's why we need imprecise probability for counterfactual analysis. And that's why this is a very new branch of research. Do calculus was very impressive, was very simple and very powerful. So people focused a lot on identifiable queries. But identifiable queries are mostly a subclass of the interventional ones. And relatively few attention was paid to counterfactual. But counterfactual is more ambitious. And in application, medical application, this is the kind of information you wanted to extract for your model. This looks straightforward if you have the P of U, but we know that in practice we don't have the P of U. So our approach is to use the empirical observation, the P of X, to obtain an imprecise specification of the P of U. This is the idea. Okay, so just to wrap up, the ingredient of a structural causal model are the graph, the equations, and the marginals. The graph is typically available. The graph is typically expressing some domain knowledge of the system, and maybe also, let's say, the exogenous part, the endogenous part, sorry, is based on some structural learning from the data. The equations might be available, and I will discuss also on how to cope if the equations are not available. The marginals, the exogenous marginals are typically unavailable, but we can do this kind of inversion and obtain them. And this is something we need for counterfactual analysis. Of course, this was not a new problem. There are early papers by Giulia Perla on special, very special case about this problem. And not surprisingly, we know that this is a Credal network inference. And Credal network inference, from a mathematical point of view, is a multilinear optimization task. So we are optimizing, we are computing the maximum and minimum of the function. This function, generally speaking, is not linear, is multilinear, which is linear if you fix all the variables apart from one. But if you give complete freedom, is multilinear. This paper was on this very special case when this function is linear. And when this linear, okay, we have linear constraints, the Credal sets constraints, the belief function constraints. We have a linear function, so we can do everything somehow. But in the general case, this is not possible. The formalism of Credal networks is helping in that. Okay, this was the example considered by Per. Let me use this. Okay, we have a number of statements, but okay, it's not that important. We have these 4 variables, 3 guys going or not going to a party, and a potential scuffle between the 2 of these guys. And let's say because of that, we can build the graph, and we have these exogenous observations. So we have data, let's say the data, and if you want, we have a joint probability over the endogenous variable. Now okay, we have some question. We have an interventional question. So the probability of B, which is a guy going on, given an intervention, and ever more challenging in orange, we have a counterfactual question because, okay, Bob eventually didn't go to the party, so B is in the false state. But what if Bob went to the party? What about the scuffle with Carlo or whatever? So you see, here we have the contradiction with this. This is a pure counterfactual. So let's focus on these queries, and let me show you how Credal network inference can answer these queries. So our problem is, we know that with the complete specification of the structural causal model with the P of U, we can answer those questions. So let me focus on the problem of computing the P of UA, the P of UB, the P of UC, the P of UOS. To compute, to obtain these marginals, we force the consistency with what we observed at the data level. So basically, we force the consistency with the joint probability of A, B, C, and S, with the 4 endogenous variables. And what you can see on the left of this equation is, remember that the structural causal model, assuming that P of U are specified, is a Bayesian network. And a Bayesian network is defining a joint probability mass function over the 8 variables we have. So we have the P of U's, which are associated with the root nodes, and we have the deltas. But the deltas are basically the conditional probability for the endogenous variable. So this is in the square brackets, inside the square brackets, we have the probability of UA, UB, UC, US, A, B, C, S. We have the joint, the complete joint. We want consistency with what we observed, with the empirical knowledge. So we have to marginalize out the latent variables. And this explains the sum over the U variables. And this is an equation. This equation is basically, it's not a single equation, it's an equation for each joint state of A, B, C, and S. And this is not really is an equation, and you should observe that the P of U's are unknown, are not numerical values. So this is basically a constraint on the value of the P of U's. This is a constraint on our marginal probabilities. The problem with this constraint is that the constraint is non-linear because we have a product between the different P of U's and is global constraint. So we would like is non-linear and is global because it's putting together the different P of U. So basically our technical effort, what we do, you see in green, these are the unknowns and they are multiplied while the empirical probability is known. Our contribution, our technical contribution was basically to extract from this global constraint, local constraint on the single P of U's. As seen in this example, obtaining these local constraints, and I can show you here. So this was the complicated nonlinear equation, and this is what we get by summing out the other P of U apart from one. And okay, in some cases you see we have to do conditioning. But basically what I wanted to tell you is that from this big equation, we can extract global nonlinear equation. We can extract local linear equations. And these linear equations on the different P of U's are defining the clear sets separately for each latent variable. And this is very good for us because in this way, you remember, this was a structural causal model is a Bayesian network, but this is a Bayesian network when we have a precise specification of the P of U for the different U variables. In this case, we don't have a precise specification. We have linear constraints, but the linear constraints are defining a polytope in the simplex, are defining a Credal set. So we have Credal sets. We have K of UA, K of B, and so on. And this is an object we know. This is just a Credal network, which is equivalent, which is a complete model of all the knowledge we have. Because the knowledge we started from was the graph, the equations, not the explicit specification of the P of U, but the manifest information about the manifest variable, about A, B, C, and S, P of X in my first example. So basically by doing that, I can obtain a proper Credal network specification. And once I have the Credal network, I can use standard algorithm for Credal networks to get the results of my causal inference. So this is one of the points I wanted to emphasize. So structural causal models are Credal networks, if you want. And okay, let me remark the fact that okay, we are coping with so-called strong Credal networks with strong, some people use maybe complete independence, and these models obey the same disseparation properties. Okay, and this disseparation is very important when you do the surgery. So let's say that we were interested in this query. Okay, because of the intervention, we have to remove this arc, the incoming arcs on the variables on which we did the intervention. And after that, we just have an observational query. Now, the query is on the Credal network. Okay, we have tools, we have inference algorithm to compute the query in the Credal network. You see? And so, let's say the query is non-identifiable, so the Credal network algorithm will give us the lower and the upper bound of the query. But maybe this is going to be informative as well. So we cannot compute, but it's not that we cannot. By definition, there is not a sharp value for this interventional query, but we have an interval, which can be informative as well. What about counterfactuals? It's really just the same, with the only difference that we needed this augmented structure. If you see what I did here was basically duplicate in this new graph was to duplicate the manifest variable by leaving only one latent variable for the model. So you see, here we have 4 manifest variable and 4 latent variable where I have the k. Now we still have 4 latent variable, but the number of manifest variable is the double. Okay, because I have the real world and the alternative world. These are what I was calling the twin network. But okay, now we just have observation on this model, and I can do the surgery as I was doing, sorry, and I can compute by standard, let me say, observational clear network inference, the result of this counterfactual. Please.
For the interval in the intervention case, that's P prime, and for the counterfactual, it's P. But there's.
No, sorry, this is a typo. No, sorry, so this is not any sorry, there's no meaning. You know, what is sometimes puzzling is that Perl is using 2 different notation for interventions. In the counterfactual is a sub. In the interventional is a do. He has a clear statement for that, which can be a bit confusing, but this was just my typo, sorry. Okay, what about the special case of identifiable queries? Okay, the identifiable queries, we know that the answer can be obtained by do calculus, and for sure by do calculus and Bayesian network inference is going to be a sharp number. In our case, we know that for this special subclass of queries, the clear network will provide us the same value for the lower and the upper bound. So it's very, if you want, in the special case of identifiable task, we have a numerical do calculus. Of course, do calculus is more efficient. Do calculus is basically polynomial, but okay, just say let us start. Yeah.
Is that an if and only if?
Sorry?
Is that an if and only if? Is it precise if and only if?
I think so, but I think so because this do calculus is sound and complete. You know, when we do that with numbers, sometimes it's messy because we have, let's say, also computer precision, so we cannot say whether this is really always the same number or is just because of some rounding. But okay, in principle is if and not if. Okay, so basically we have algorithms, and our algorithms can do something very simple because they take a model without the P of U and with the data as an input, and they give you back a clear network. And then with a clear network, you can compute the queries. Is this general? No, it's only for, of course, for the Markovian models. A Markovian model means a latent parent for each variable is very easy. We extended this to a class of structural causal model, but not to all of them. Basically, we call this model quasi-Markovian. And the idea is that the latent variable is like the Markov blanket, but okay, it's a specific concept, is separating the U variables. So we have group of single U variables. We have software for that. Crema was a software, was a library, Java library we implemented for clear network, general clear network inference. And should not be surprising that the library for causal analysis in this approach is built on the top of Crema, in the sense that this library is just doing the conversion and eventually is using the clear network algorithms for the inference. But in practice, you can compute counterfactuals. There is a good, relatively good documentation. You can use it in practice. Okay, these are some experiments. Again, clear network is NP-hard, very hard task. There are very good approximation, which are these dotted lines. Exact inference can be very slow, very challenging, basically unfeasible if the model get larger. But okay, for let's say with these approximate techniques, we have a very good accuracy. So we can, let's say, assume that the intervals we get from the clear network are really very, very close to the real partially identifiable bounds of our causal query. Okay, short is not black, but this was related to Earth's point. We cope with cradle sets on the latent variables. Okay, we have these two, well, complicated, but not too complicated algons. And these algons are basically defining the cradle sets on the root variables. They are defining them by equality constraints. Generally speaking, we need the linear constraints to define these cradle sets in cradle networks, which are inequality constraints, linear constraints. Our constraints are equality constraints. And we are basically defining a special class of cradle sets which correspond to belief functions, which is another, let's say, family, if you want, less general family, but okay, more general than this class of constraints, family of generalized probabilistic models. Some people use Dempster and Schaeffer. They were originally, okay, Dempster and Schaeffer did contribute to the theory of evidence, or to the Dempster-Schaeffer theory, well, from different perspectives. If you want to think, the most interesting approach from our perspective is the one of Dempster, where he considered the so-called multivariate mapping, which is exactly the same, almost the same picture used this morning by Fabio for the cradle semantics. But, okay, I guess from between you there is some belief, people with experience with the belief function. You will kill me because my definition is very quick and dirty, but let's say a probability mass function is distributing the mass of probability over the different singletons. A belief function is distributing the probability mass over subsets, not only singletons, but subsets. And these subsets can be overlapping. Okay, and okay, you can see that in the sense that you can have two spaces. This is the space, let's say, of our variable, and you define, okay, now this is a space where you define a probability mass function. Then you have a mapping which is not one-to-one, but is one-to-many. And so this probability, 0.3, 0.2, and 0.5, refers to a set. And the different sets can be overlapping. And because of that, you have multiple specification, multiple probability mass functions that are consistent with your belief function. This is at least, let's say, the perspective of a cradle set guy. So I consider belief function as a subclass of cradle sets. Of course, the machinery, the conditioning, the combination rules used by people in the field of evidence theory are also different. There are different motivation. But let's say, roughly speaking, the cradle sets we are considering are belief functions, and this is not surprising because what we are doing is like using the inverse of the structural equation to moving the probability mass function over the x back to the user. And as this function is not one-to-one, but is many-to-one, the inverse is one-to-many, and so that's why the cradle sets we get are belief functions. This is nice to me. It's not helpful from the computational perspective, but I think this is an interesting debug. Okay, it took to get 20 seconds to do. It took to me much more time, but it's nice debug. Okay, stop. End of the intermezzo about belief function. And there is still an open question because the machinery I described to you is only suitable for a special class of structural causal model when they have this quasi-Markovianity. So when these models, we can extend it. Sorry guys, I'm lost. How much time do we have or more? Sorry? 35. Okay, yeah, perfect. Yeah, I was just okay. And let's say if we have a general model, which I would call non-quasi-Markovian. So if we are not in this special class, what can we do? Okay, basically, we have to merge together different exogenous variables. This is doable. There is a point because you see, okay, now this is a kind of non-linear object, But okay, we are regarding this as a single probability, and by doing that, okay, we are forgetting the fact that these two variables are unconditionally independent. You see that we are assuming that their joint probability factorizes, but then when we merge them together, we are forgetting this independence. You can prove that because of that you are not losing precision in the inference, but okay, this is just a detail. What I want to emphasize is the fact that by doing that, you can get a larger variable with a higher number of states by definition. And sometimes this can be an issue because, okay, the complexity of the Critical network algorithms is affected by the size, by the topology of the network, but it's also affected by the cardinality of the states and even the space you need to describe your object. So we were, let's say, not fully satisfied. And let me say this: this is going to be quick. But we also are interested in the case in which we don't know the equations. So the structural equation, we have the graph because the expert is providing us the graph, but we don't know which ones are the mechanism. So which one is the equation? And I think this is also somehow inspired by the imprecise probability, because it's very common that, okay, in imprecise probabilistic approaches, you have multiple candidates, you have no reason to choose one of them. Non-imprecise people just pick one of them according to some neutral strategy. And the imprecise guys say, okay, let's take them all. Let's be conservative. Of course, this makes things more complicated, but also more exciting. And somehow, this is what we can do also when we don't know about explicitly which are the structural equations in our model. Let's say that here we have A and B, which are the two endogenous variables. We have a latent U of B, and we are asked to quantify this equation. Let's say that A and B are Boolean or whatever. Okay, for each U, okay, F, this is a deterministic relation. So for each U, the relation between A and B, between B and A and B, should be deterministic. Okay, but if you have two Boolean variables, how many deterministic relations can you enumerate? I would say 4. We can have, if B is the deterministic function of A, B can be always 0, B can be always 1, B can be equal to A, or B can be the negation of A. We have just 4 alternatives. Because we know that these relations, so this is the CPT, the conditional probability table corresponding to the just 4 deterministic relation I mentioned. Which one is the right one? Are there some of them that should not be considered? At least in principle, I don't know. So let's pick them all. Let's use the U variable to enumerate these 4 possible quantifications. And in this way, we get a conservative specification of the equation. This is the most conservative equation we can consider, because U is enumerating any deterministic relation between B and A, and generally speaking, between B and its manifest parents. This is good. And even better, in some cases, we made them some knowledge, which is removing some of these mechanisms. Okay, this was the party example. In the party example, we know that Bob goes to the party, fund us, or whatever. So this is not acceptable, and this is not acceptable. So 2 of the 4 states of U are not acceptable. But okay, in the worst case, we have to pick all the 4 of them. The issue is that, okay, in general terms, this can provide a very large conditional probability table. So the equation, the states of U, we need to enumerate all these mechanisms can be exponentially huge. Locally, with respect to the parents of Y, here we are between X and Y, but still can be huge. And so you see, we have a clear machinery, we have a clear representational result, but okay, we might have computational issues because this can make the size of our latent, the number of states of our latent variable very huge, And because of that, our neural networks algorithms can be slow. And okay, in fact, this was an application. Actually, it's not the more optimistic application I can show to you, but okay, this was interesting from my perspective. This is a kind of causal graph we derived together with experts. This is related to, let's say, palliative cares for cancer, oncological patients. There is this association in Switzerland, very close to our institute. We derived this causal model. There are many factors, and basically, what the purpose of this study was to determine the preference of a patient with respect. These are terminally ill patients with respect to the place of death, which can be home or can be hospital. And there are a number of factors. Okay, what we wanted to study was basically whether an intervention of some of these variables might have an impact on the variable of interest, which is the place of death. And to do that in a proper way, we need a causal analysis. So actually what we wanted to compute is the probability of necessity and sufficiency for the target variable, and the target variable Y is the place of death, given a possible intervention of or this variable or this variable or this variable. In particular, you see related to awareness of the patient or the family of the patient, and this is basically the role of the association. Okay, simple. Here we don't have the exogenous variable, but the exogenous variable basically we assume Markovianity. So we have a latent parent for each variable. Here we don't have the equations. Okay, it's not a problem. We can do the conservative enumeration and just show it to you. Here we have the data. And only very strict privacy relation, but basically we have a joint probability of it. So we have the same ingredient I just discussed to you. So in principle, we can compute these counterfactors, this is a counterfactor probability, but in practice we cannot, because the model is very huge. Now I don't remember, but there are some variable with relatively 2 or 3 parents, but the cardinality of this variable is huge. So the number you get in this formula is really huge. So it takes a lot of time. And that's why we started to work in more efficient approaches to this kind of inference. And this is going to be, I see you're tired of one of the last topics. So we are basically looking, we know now that the problem we have to solve is a clear network inference, but we need something faster and more scalable to get the result. And let's say the idea we explored was related to the fact, okay, we have observation, we have exogenous observation, and so far I was just focusing on this data set. But we can intend this data set as a data set involving also the latent variable, the exogenous ones, which are missing. And they are always missing because they are latent by definition. So in the sense, this is a asystematic missingness. It's what we call missing, a special case of missing at random. And these are the hypotheses for the classical expectation maximization algorithm. The expectation maximization algorithm basically is again, Dexter, is an iterative procedure that allows you to complete the missing data. So basically what you do is just to start with a random initialization of your model, you guess some probability. Given the probability, you replace this start with the expectation for the different values of the missing variable in the model quantified with these guessed probabilities, and you get number counts. They are fractional, not integer, but okay, you can use the count to retrain the value of your model. In this case, it will be a structural causal model or Bayesian network, and then you do that iteratively until convergence. This procedure is not to converge to a maximum, can be global or can be local, of the likelihood function. So it's a kind of maximum likelihood. But okay, when you do maximum likelihood with complete data, we know that the likelihood is unimodal. So there is the maximum is the global maximum. So it's exactly what you are looking for. Here, in principle, you can find a local maximum, which would be a suboptimal estimate for this function. The good news is that you can prove that the likelihood of this model, in spite of the missingness, is unimodal. And so you always get a global maximum of the line. The estimator you get for the probability of the U after convergence is a global maximum. And you can prove that the maximum likelihood corresponds to the point of your Euclidean sets. So after convergence, you get a P of U. This P of U is a global of the likelihood, and because of that, this P of U belongs to the Euclidean sets. So what we are doing is basically sampling the P of U from the K of U. We are sampling points from the Euclidean sets. And what is surprising is that by doing this sampling, we can obtain very accurate results. So we don't need to run the complicated Euclidean network inference. We have to run n times Bayesian network inference, because now we have a collection of P of U's. But the Bayesian network inference, we have multiple points, but then the interval spanned by these points is a very good inner approximation of the real interval. And this is true with a very low number of initialization or samplings. Please.
Which is faster, running the parallel match mode or?
Okay, it depends on the neural network algorithm. But okay, I would say, generally speaking, the Bayesian network inference is always faster than neural network inference. Bayesian network inference should be multiplied by the number of points you sample. But as we get good approximation, good confidence with few points, Bayesian network is faster. And this was our context. Okay, and okay, we have, sorry, I forgot to remove, but okay. This basically was, let's say, a confidence, let's say, an inequality to characterize the quality of our coverage. So the fact that we get high credibility can be formalized. Of course, here we are doing some assumption, because we are sampling uniformly from the initialization of the EM, which is not like sampling uniformly for the real data set. And okay, now we are improving these results, and still, and also, okay, the empirical results we're getting are in line with that. So basically, we find very, very good intervals with very few points. And okay, in the special case of identifiable queries, by definition, if the query is identifiable, we always get the same point, because we are getting an inner approximation of the interval. But if the interval is a point, we have an inner point of a point, and so it's always the point. So the hypothesis we want to test is when, after how many times we get always the same point, we can decide that this was really an identifiable query. And the number is variable, as you can see, it's 9 runs or whatever. Okay, depending on the credibility you are looking for. Okay, okay, we did some tests. Okay, this EM procedure is embedded in Credici, which is our library, and these are the results. So you see, these are counterfactors. Counterfactors are partially identifiable by definition. Let me say like that. These are the intervals we get, and okay, they are intervals, but we can see a clear dominance for this one, which is the effect of the association. So this was important on the level of, okay, the society for our, let's say, local environment to justify some action. Okay, but this just, if you want, is a very first, from our point of view. There are people doing already doing a lot of causal. Don't know whether causal. This is called causal machine learning. It's more probably causal analysis. But to draw conclusions which are, in a sense, more solid than what you can do by means of traditional machine learning. So this is, if you want, is the message of this application. Okay, I think I will finish a bit earlier because I think everybody, okay, let's see also if you have a question, maybe also this can be a bit more relaxing, but I just want to say something about explainable AI as I think a very promising direction for causal analysis. Explainable AI is not new. I told you when exactly in the same moment. Oh, I miss. Fabio, if you want to say your question, but let. Oh no. Okay.
Well, I just wrote a question, but so is this a simple question? Can you hear me?
Yes. No, I think I thought about that. I think for some people it's obvious that counterfactors, I don't have a proof. Probably is very simple to prove. I think it's related to this separation, but this is related to this twin network structure. So basically, I think I don't have a formal proof, but you know, the counterfactuals should be, in fact, I was writing non-trivial counterfactual because I'm sure you can invent the counterfactual which is identifiable. But because you need basically this auxiliary structure, you always have confounders. And the confounders are basically propagating the imprecision.
Oh, I see.
You see.
Okay, so it's non-trivial in the sense that it's non-trivial in the sense that it has to have some conditions, right, to happen.
Yes.
To hold.
I haven't tried, but I would guess that I can invent a counterfactual which is identifiable.
Okay, thank you. No, that's fine. All right, thank you.
Okay, thank you, Fabio. And okay, regarding explainability, let me say that people, okay, is already doing a lot of explainability. If you are looking for techniques to explain your classifier, probably line is going to be one of the first results. Is very popular, is model agnostic. It means that it can explain any classifier and is really very flexible. Continuous variable, discrete, hybrid, whatever, computer vision, natural language processing, whatever. Okay, the idea, okay, this is an example in computer vision, but is general. The idea of Lime is quite simple. So I have my classifier. My classifier is telling me that this is a frog. Yeah, let's say like that. This is a frog with probability 0.54. Okay. I want to explain not the general behavior of my classifier. I want to explain why my classifier, my neural network, is telling me that this is a frog with some probability. What I can do is just to start from this instance, and this instance, let's say, is the feature, is the set of a feature, and the classifier is a function giving me the class corresponding to this feature, to this observation of the feature. I have the feature, which is the image of the frog, and the class, which is the result, which is frog. Okay, I don't want to do the explanation directly at the level of the neural network, but I want to use some different, simpler classification technique. But I don't want to retrain a complete model because I'm not interested in a general explanation, global explanation of the classifier. I'm interested in this image. So I create a kind of surrogate synthetic dataset. And the dataset is based on this image of the frog and on perturbations of the image of the frog. For instance, here the perturbations are done by covering different parts of the images. You know, machine learning needs annotated data. So it's not enough to, I can generate as many images as I want, but I need an annotation. I need an expert telling me that this is a frog, this is not a frog. Okay, but these are synthetic data. I'm not using an expert, I'm not using the human annotation, but I have my neural network already trained. So every time I take my picture, I do a perturbation, I cover part of the picture, and I ask my neural network whether this is a frog or not a frog, or whatever. And I keep doing this kind of perturbation. So in this way, I create a new data set, which is now annotated. Annotated by the classifier, but annotated. And now I can query these different images, and you can see, for instance, here the results. So I can, for instance, check which are the perturbed images that remains a frog and the ones that are not anymore. So you see, for instance, that by covering these parts, the probability of being a frog, sorry for that, is increasing. By covering this part in the second example, the probability is decreasing. And this is considered to be an explanation. Please.
I think of this as an out of distribution robustness because I'm changing the...
Yes, yes. If you want, you are interested in check how your final goal is to see how robust is the output in spite of local perturbation of the image. I think it's done in a very systematic way. So it's really just by doing different random perturbation and checking which ones remains close to that. It's very powerful, but okay. To be so powerful is based on very simple ideas, and this is what people consider an explanation. And what is a bit disappointing from my point of view is that some of these explanations are called also counterfactual, because I'm considering the alternative world where the frog has lost part of his body or whatever. And I think you can see my point when I say that this is not a genuine counterfactual, because it's exactly the same situation. Okay, now I have a lot of slides too. It's the same situation of the Simpson paradox. I'm just comparing two different conditional probabilities. So this is what Line is doing. Now there is another approach to explainability, which is based on the Shapley values, which are kind of I think is more so sophisticated, but still is not a genuine causal analysis. And okay, basically what I wanted to say is that this the current techniques for explainability can be very flexible, very powerful, but in fact are not based on the causal analysis. So I think a very new trend is to look for causal explanation based on counterfactual analysis. The problem is that the kind of inference you need for such analysis is complicated. I wouldn't know how to define easily a spatial causal model for this, let's say, classification, image classification task. Okay, this is also a very famous example. So in this case, the classifier is giving you the right answer, but you might need to know why I'm getting this answer. Okay, you can run Lime, and Lime will tell you that the answer is ASCII because of this white part. So basically, from the data, for some reason, the classifier learned that if the background is white, I'm on some snowy place. Sorry, and this sorry, I cannot distinguish an ASCII from the wolf. This is an ASCII, or maybe, I don't know. I don't know, but okay. Anyway, I think there's another example with fishes, and let's say the classifier learned from the background that there is a fish. If there is a fish, there is a man in the background, it means that it's a fish or something like that. Okay, needless to say, I think that explaining the output of observational classifier is something that requires causal analysis. I don't want to enter the details. The same applies also to reinforcement learning. And okay, explainability of reinforcement. Reinforcement learning is basically about this morning lecture of Fabio about planning, is trying to learn the strategy from plane, by plane, by running, by interacting with the environment. And okay, one approach to this Bellman equation discussed by Fabio this morning is to learn this Q function, Q value function, which is actually how good is a particular action given a particular state. And okay, basically we can consider an agent which is greedy, which is always taking the action that maximizes this quality value for the given state of the world. And this can be used exactly in the same spirit of Lime to consider the difference between, okay, I can do a perturbation of the feature, I can compute the different covariance, I can see how this is changed. But again, this is not really a counterfactual analysis. So I'm pretty sure in this way, people is generating these nice pictures where you can see, for instance, this is an Atari game played by an artificial intelligence, which is not, yeah, bricks, some old game, artificial. I don't know if you never saw this reinforcement learning play and learning very quickly how to play in a smart way. And you see the blue parts, the blue areas are saliency maps. So you try to measure which is the important part. Exactly as in the case of the frog, we were looking for the important part of the image. This is the important part of the space for getting this particular action. So it's a kind of robustness analysis, but again, we are considering two different words in a separate way. So this is not a counterfactual analysis. Okay, so this was basically my point. I think this is a promising and somehow not so impossible direction of application for this kind of causal analysis. Something I wanted to do with some colleagues relatively soon. So I think I can really stop. If you have a question, I'm happy to answer, but I think I can really wrap up. And my point was really that in these causal models, because of the latency of these exogenous variables, the relation with imprecise probability approaches is clear and is very strong. So I think this is really a natural application for this kind of this, and it's very promising because is one of the few techniques to go to this counterfactual analysis. The other guys, if you read the paper of these other groups, they say, okay, this is the result, and then let's go for polynomial programming. They don't care actually about it. In some cases, they don't care too much, but just say that the background developed for independent reasoning in this field can be really exploited for this kind of application. So I think it's very open direction. If you like this stuff, you're interested, let me know, but also consider, and let me just close and say that the key is the latency, so that I understand that you should be somehow interested in these imprecise probabilistic approaches. It can be the case that you need that because of sensitivity analysis. It can be the case that you need that because, as I was doing for a lot of time, you cope with expert, you want to capture the knowledge of the expert in a reliable way. Maybe for some reason you cannot completely trust, so you want to be cautious. But if you are missing of your data, we have some incompleteness mechanism, it's very likely that these techniques can help you a lot. Let me stop with that, and thank you for the attention, especially in this late part of the